So here we have the concept of aligned and misaligned memory. So the way that the CPU is designed, it was into basically with consideration that it's gonna be reading memory like 32-bit at a time. So that's like the most performance and most efficient way for a CPU to handle the memory. So that's one way to think about it, that every time that we are writing to our memory, we are doing in 32-bit chunks. So every time also we are reading, we are doing in 32-bit chunks. So in that way, the CPU can be more efficient because that's kind of like like an assumption, and based on that, it can actually perform faster. So that actually depends, and we have different sizes. So for example, in MIPS we have word aligned. That means it's 32 bits. Every like that like array that we talked about, the size of each unit is 32-bit or 4 byte. So that's what we are dealing about. But like we have 64-bit also, which is very common, and it could be in different sizes. But in general, if you are looking at these memory addresses here, that you are going from 0 to 8, and if you are in a 32-bit system, you are seeing that the first one is aligned if you are starting reading or writing from here, because you are going um, four, basically 4 bytes, and the next one gonna be at 4, so you go 4 bytes here. If you are going to 64-bit, that means every time you are reading or writing 64-bit at a time. That means if you start from here, you're gonna go all the way to beginning of 08. And basically that's the idea, and you never want to cross these bonds. So here is some more detail. Basically what we talked about, that the addresses at 32-bit aligned or word aligned gonna be always starting with 0, and every time we are adding 4. So the next one gonna be 4, the next one gonna be 8, because each time we are reading 4 byte at a time. And basically that's the idea. And if it's a misaligned, so that's another term you should know, that means that we are crossing these boundaries. So if you are starting somewhere here, let's say at 1, and you're going 4 bytes, that means you're passing this 4, and basically that's a boundary. So for CPU to do that, actually it cannot do this one as a one read. You have to read like these bytes separately, and that's very inefficient. And how do you know if it's aligned or not aligned? Basically, you have, for 32 bits, it has to be multiples of 4, your address. So this memory address that you have, if it's a multiple of 4, it is aligned. If it's not, like a 3 or 2, basically it's not aligned. And how do you know? You can look at the end, the last digit. If it's 0, 4, 8, or C, that means it is aligned. It is multiple of 4. If you are looking at binary, the last 2 digit gonna be 0. So if you have here like 1, 0, 0, that is aligned. If you have a 1 here somewhere, that is not aligned. And if you convert these hex numbers to binaries, you're gonna see all of them are have zeros, and those are the only 4 that have 2 zeros here. So basically that's the concept. So we are always using in MIPS, in this course, we are always using 32 bits or word align. So basically this pattern here. So here we see that the amount of like on your memory space or address space that you have on your memory. So we said that we have like this kind of address, and each of them are 32 bits. So if you see, it's 8 hex digits, and each of these is 4, so 8 times 4 is 32. So each address that we have is actually itself, the address itself is 32 bits, and the content is also 32 bits. So that's what we are dealing with, right? So in your address space, if you have all the numbers, and if you list all of them, that means the amount of the memory address that your CPU can basically access, right? Because that's all the addresses that you have. So like if I want to say another example, like let's say if you say you have an array that the index can be only 1 digit. So that means how many total different um, location on the array you can access if it's only one digit, the index. It's gonna be basically 0 to 9. So you have like kind of like 10 different location on your array that you can access roughly. And here is same idea. So you have your address space is 32 bits. So basically there's a limit, right? So the largest number that you can represent by 32 bits, it's basically if all of them are ones, right? So F is basically 4 ones. And this is going to be the largest address that you can have. So your smallest one going to be all zeros, and the largest one going to be this. And if you convert that to decimal, it's going to be this number. So this is, yeah, I think billion, 4 billion, I think. Um, and basically, so that's the largest number. So, but what is that unit for that? So if you have this many indices in your, or if this many different addresses in your memory, um, each of them is 1 byte, right? Each of them that we are dealing with, it's actually 1 byte. So if you put this one actually and divide it by 1024 to make it kilobyte, and then again by 1024 to make it megabyte, and one more time to do 1024 to get it gigabyte, that's gonna be roughly 4 GB. So that's it basically. With 32-bit address, you can um, basically refer to 4 GB of memory. And there is this note here also. So basically, like a kilo, when you say kilo in the SI unit, it's 1000. Is 10 to the power of 3, actually 1000. In binary, we are dealing with 1024 because our base is 2. So that's gonna be a bit different. So you see, actually, if you get like a 4 GB like a flash drive, when you actually attach it to your computer, and you see it's actually like 3.9 something. So that's one reason that they're doing it in SI unit. So that's gonna be always 1000 times 1000.